I'm Erik. I'm Senior Vice President of Engineering for the Sesame product line at ITRenew. So let me give a bit of background on ITRenew. We are in the circular data center business. So the business that I'm responsible for is the Sesame product line. We also operate products in decommissioning and of data sanitization, decommissioning work. We also are doing designs for edge solutions, so either small scale data centers or explicit kind of outdoor edge IoT types of solutions, all based on scalable data center technology that's being repurposed for additional use cases. So we have long-standing relationships with a number of the key hyperscale players, and that allows us to create a bunch of leverage for our downstream customers. Right. Then the diagram right here, just again very briefly, overviews the ITRenew business. So we've been in business for over 18 years. And have established relationships, in some cases exclusive relationships, with most of the largest hyperscale service providers. So a number of the companies are shown there in the logos. And what we do for them primarily is data decommissioning, data sanitization, chain of custody. So basically we take care of everything that happens to the equipment after it leaves the data center. But because of the length of our involvement, we were also now involved in their MPI, when they first deploy the hardware, to prepare for eventual kind of decommissioning and reuse, right? And then the core of the ITRenew operation, so we have 12 facilities worldwide where we process between 40,000 and 70,000 servers per month from our various kind of upstream clients. And what we do is repurpose that equipment into several outgoing streams that I show in the blue bubbles in the center of the chart. So the product that I'm responsible for is Sesame by ITRenew. And what we're doing here is we're taking rack scale servers and networking storage equipment from our hyperscale clients. And we're building rack scale solutions for service providers and enterprise SaaS companies. So we're basically taking data center equipment, recertifying it, refreshing it, and creating data center rack scale appliances. And then the second case is what we call edge solutions by ITRenew. And what we're doing here is we're taking the individual servers, the individual boards, the networking devices, and refashioning them into form factors that are not data center racks. So for example, IoT gateways, edge gateways, 5G wireless router, where we're taking the core technology, the CPUs, memory, motherboards from data center equipment and refashioning them into different form factors. And then the last two are kind of the traditional businesses of ITRenew. So we also have a business in componentry that we extract from this equipment. And then finally, for any kind of residue material, we perform a responsible recycling kind of task, right? So 4 different ways that we process the equipment, with the most circular, kind of the most attractive, the highest value recovery being the rack scale solutions. So that's what I'm going to talk about some more today. And so the alluding to the title of the talk, kind of open, uncomplicated, we think that in this stage, so I don't know about you, but I've been involved with open software and open hardware for essentially my entire career. So over 20 years of experience in openness and industry collaboration. And we really think that now is the time, or the last 5 years, or even a further acceleration on trends that already existed, and where the leverage of all that has gone before is available to a very wide community, right? So what we're doing with Sesame is we're creating pre-configured plug-in ready rack scale solutions based on open architecture technology and utilizing open source software in ways that I'll describe further. But what we position with our customers, no assembly, no guesswork, no army of engineers that you have to hire and train yourself. We're bringing the leverage of 5 years, 10 years, sometimes 20 years of open innovation, of ecosystem innovation to be immediately useful in the data center, right? And so what is the difference from hyperscale in the normal instance, or the difference from using a cloud? So a number of the advantages that the large cloud providers have are shown on this slide, right? So there is a massive budget pool and a talent pool to draw from, right? They have, in some cases, hardware engineers on staff, always software engineers on staff. They're regularly refactoring and rebuilding technologies to optimize for their specific workloads, right? And so that allows them to take advantage of the cost benefits, the efficiency benefits, the most advanced technology. It gives a lot of flexibility with the scale that they have, right? Underutilized hardware here and highly utilized in another place. They can move workloads around and so on, which combines to give a lot of the lowest costs, right? And so what we're trying to do with Sesame is bring those advantages to companies that are not at the scale and do not have the budgetary investments that the cloud providers do. And what we're hoping is that customers will then be able to use the resulting kind of cost savings, the resulting efficiencies to create and deliver more services, to grow your user base, kind of respond faster to customer needs, and accelerate business growth, rather than using the money that comes in as revenue and investing in technology and infrastructure, right? So we're trying to bring the leverage that the technology industry, specifically that the hyperscale cloud industry has made investments in, that is brought into the open community, and we're making ways to consume that out of the open ecosystem, right? So I want to talk in a bit of depth about how that works and what the pieces of that are. So what I'm showing here is 5 aspects of the open story, or the open kind of ecosystem. And I'm going to go around the chart here and discuss each of them in turn, right? So the first one is design, engineering, and product expertise for hardware design, right? And there are many investments here over the years. As a computer hardware today is much more powerful, much more scalable in terms of putting large clusters and large applications of machinery together, but also more inherently reliable than systems were 5 years ago and 10 years ago. And that's due to investments in hardware engineering and product designs and so on that significantly improve both the performance in terms of how much workload, but also the performance in terms of reliability, right? So there's an incredible amount of investment that has been made, and that investment can be tapped by the open hardware community, right? And then similarly, you'll see it's actually the same text for software as it is for hardware, because really those same trends have been used also in the software industry, right? That the software folks, kind of open source as embodied as Linux or Kubernetes, other types of stacks, was discussed more aggressively or earlier than open hardware, but it is ultimately the same philosophy, right? It's a group of engineers, a much wider group of engineers with a wider set of experience, a wider set of expertise applied to rigorous commitments to quality and interoperability and reliability, right? Software reliability is not immediately identical to hardware reliability, but the end result for the customer is very much the same, right? Because these software components are made available in the open community, they're vetted by a number of different vendors, by a number of different customers. For example, the Kubernetes community, the CNCF, that is the kind of the core organized community around Kubernetes, has 170 end user participants. So it isn't just the software vendors or the folks creating the technology, it's also the folks operating and using the technology that are giving feedback to the process and so on, right? And all of that leads to a massive increase in interoperability and quality per se. Very similar to the types of benefits that we've gotten over the years in the hardware industry. Then the next piece of it, in the bottom left corner, we talk about a very wide dynamic range of skills that are applied to this problem. And it really is, so I'm a trained computer engineer, but I've done much of my my work in this industry in the software and in the design space. Officially, I'm a hardware designer, but still spend a significant fraction of my time on software and algorithms and so on. But there is this wide dynamic range. So as I say in my text here, from capacitors, the various colors on capacitors and voltages, through consensus algorithms, the CAP theorem, et cetera, distributed replication, eventual consistency, all the way to cognitive load, the responsiveness of a user interface or the complexity of a user interface where operators are trying to make decisions for 1,000 or 5,000 machines at a time, right? So there is a lot of engineering breadth that's involved, right? Just within my own team at ITRenew, I have electrical engineers, mechanical engineers, as well as operating systems engineers and solution architects, right? So there's a lot of different expertise, a lot of diversity of background and skill being brought to the table. And that's true across the hardware and software boundary. And the next piece, the DevOps revolution, if you will, in many ways, aspects of this have been building for many years, but that collaboration from the design phase, from the whiteboard, from the factory floor, from the CI/CD pipeline, all the way to the folks who are operating the software and systems, right? The fact that we have now integrated across that partnership. Now the operations teams have integrated with the development teams. There's no longer this big divide between the folks who write the code and the folks who operate the code in practice. It's very similar when you add hardware to that as well. The folks who design the hardware versus the folks who operate the hardware, as well as the interactions with the various software layers. Right? And then finally in this particular chart, we have automation, analytics, and machine learning for all the things, right? And this is very true, becomes more true kind of every day. If you're operating at the level of 1,000 nodes running 2,000 applications, or 10,000 nodes running 2,000 applications, the efficiency and effectiveness of that system is dependent on the machines doing most of the work, right? Making decisions at millisecond, sometimes microsecond level, and then being informed by, again, the DevOps and the design skills. But in a lot of cases, once we build a cloud, we deploy it and we want it to run kind of largely independently, right? So there's 5 aspects to this kind of open revolution, and each of them powerfully kind of combine to enable today's ecosystem. Right? And so let me then briefly take it apart again in terms of hardware and software. And I'm going to talk about basically the same 5 categories, right? So we talk about in hardware, open compute hardwares, the subject of this community, this summit. I've been involved in the OCP community since the early days. Before that, was involved in numerous bilateral and sometimes multilateral industry standards organizations. So I've definitely seen the power of the community working together. We've gotten more flexibility because it's standards based. We can plug things together. we've gotten massive increases in density because we've been able to work together. We've co-designed storage and networking with servers. Many years ago, those were vastly different disciplines. Today, we're all working together for the same kind of optimized high density goal. Then we have optimized power. In this case of the hardware, this is about the number of electrons that are being used, right? So rack level power is more efficient in terms of the number of components. So there's less power supplies in the rack, and the power supplies are individually more efficient. So it's both less cost, more efficient, and fewer points of failure, right? So it really is the power of design improving on all dimensions, right? We improve the efficiency, we lower the introduction cost, and there are fewer points of failure by the application of design principles that have been learned in the hyperscale and similar environments. Then the next one is optimized cooling. So this is directly related to power. So every electron that goes into the rack is dissipated from the rack as heat. So that means taking advantage where possible of free air cooling in the data center, minimizing hotspots within a rack. So the best case is that the rack very cleanly takes in electrons through a very small wire, or the straw of electrons coming in, but dissipates the heat in a very diffuse way, right? So that you don't end up with hotspots, you don't have to mitigate against the cooling. And the best, the most advanced data centers in the world have worked this through explicitly free air cooling, where there really is no need to additionally cool the air before it's applied to the system. Just using ambient temperature air is sufficient, which is essentially the holy grail of cooling is not to have explicit cooling, right? And then finally, but often maybe considered as last minute, is the streamlined maintenance, right? So in the case of hardware, this means toolless service. You don't have to carry around a toolbox. You don't have to search around of where you left the Torx 8 last week. It's all managed, and maintenance can be done with simple, with basically just your hands, right? There are companies also looking at doing this with robots, but this is again in the same way as optimized power. When there are less components, the components are more easily serviced. It means less cost up front. It means less cost during service, less cost during troubleshooting and updates, right? So these are really 5 pillars that everyone in the OCP community should be quite familiar with, of the benefits of open hardware. And because of the way that I formulated this talk and what I said in my slide with the 5 pictures, I brought the analogy to open software with basically the same 5 pillars, right? So flexibility is straightforward. I've already mentioned it, right? By using APIs, standardized APIs, interfaces between components, contracts between the functionality of software components, we get much of the same benefit that this drives in the hardware world, right? High density computing. So for software, this means, again, API-driven software, automation, the machine learning that I alluded to in the previous chart, or maybe just statistic-based management of the systems, all of which allows more software, more workload to operate per square inch of silicon, right? So high density computing is also enabled by advances in the software stack, right? Optimized power here, taking a slight liberty, if you will. So it's not the electrons of the previous chart about hardware, but this is about the functionality. So here I'm using power to mean functionality of software packages. So the stacks of software systems that are deployed today will be sometimes millions or tens of millions of lines of code that are deployed with a single command line, right? And because of the efficiency of that design, the carefulness, the thoughtfulness that have gone in, it operates with the same way as the hardware. It's more efficient, it's less cost, there are fewer points of failure, even though there is proportionally more software running today in data centers than ever before. So there's certainly more lines of code of software in the data center today than there have ever been. But because of the way they're built and integrated and designed together, it actually produces more end result, more simplicity than before. Optimized cooling. So this was cooling in the hardware way. Here I'm talking about validation. So software, continuous integration, CI/CD pipelines are really the cornerstone of making sure that the less points of failure, the integration of these stacks operates effectively. So if we weren't automating our integration pipelines, our test pipelines, our delivery pipelines, then we wouldn't be able to deploy the layers of software with millions of lines of code each. But because we're using the machines to do the heavy lifting, if you will, that optimized validation applies. And then finally, similar to toolless application in the hardware space, there is streamlined maintenance of software through APIs, through DevOps design throughout, ease of troubleshooting, ease of updates, right? It's just as important in the software space as it is in the hardware space. Even 5 years ago, it would have been unthinkable to upgrade your infrastructure software every month or two, perhaps 3, right? And that's done routinely today, whether it's vSphere or Docker or Kubernetes, right? There are infrastructure level upgrades that, that folks would have been afraid to do years ago. Okay. So hopefully I've characterized that the benefits occurred to both hardware and to software, bringing it all together in a single kind of visual here. So what I'm trying to show here is taking agility, flexibility through hardware design, physical design, our cloud cities, the physical plant of our systems, through to the various stacks, whether they're sometimes hardware stacks, but often software stacks that are more conceptual in the different colors, different flavors, if you will, in the center here. And we're able to build something much more powerful as a result, applying that creative flexibility to creating a more powerful whole. And that's true from hardware all the way through to software stacks, right? So finally, just bringing it back as a reminder to what we're doing at Sesame. So we're building on the benefits of that open hardware and the benefits of that open software for our customers, right? So we're going to deliver a rack scale solution. It's pre-tested, pre-qualified with a number of different software stacks. And that means that a customer can just roll the solution into their data center and begin operating workload, right? We have 3 solutions that we're discussing for this year: Sesame for open systems, Sesame for converged infrastructure, HCI, and then later in the year, Sesame for AI and machine learning. Each of these optimized for those particular workload scenarios. And then, as I've motivated, we're presenting this with the software community. This is the software ecosystem of Kubernetes. This is a CNCF landscape, giving just a sense. This isn't even the complete picture, but it is nearly complete. But this is the number of companies and projects that are involved in the total system. And we're bringing those all together, the power of those, for the racks that we deploy for our customers. Very briefly, so I can finish up, this is a conceptual view of our open systems rack. We have up to 45 nodes within a rack, and a couple of different flavors of nodes, including infrastructure for operating system Kubernetes, and then workload nodes, compute and storage. Integrated and pre-validated against a number of those software infrastructures, which wouldn't be possible if it wasn't an open community, and we were all sharing in the design and building. So hopefully I've motivated the power of open hardware, the power of open software, and given you at least a hint of how we deliver it in Sesame. If you're interested in learning more, find us in the virtual booth here at the OCP Summit. Find us on our website. Contact us on Twitter. We're reachable in many ways. And I'll just make one final reminder. Please do reach out to us. There's a lot of details in here. And remember that ultimately clouds are built by people. And that's really why we get all this leverage. So I've really only talked about technology, but all of that is enabled by this vast ecosystem, which is kind of engineers, operators, implementers around the world. All right. So don't forget, clouds is people. All right. Thank you so much. And let me know if you have any questions. Feel free to reach out and contact us.